Hi, in this lecture we're going to learn about the history of modern astronomy. In order to do that, we're going to actually start from the very beginning um, and go all the way up until the 1920s, where we finish off with Albert Einstein. Okay, the first model we're going to talk about is a geocentric model. And this model kind of makes sense to me. I mean, if I'm just a sheep herder and I'm walking along with my sheep, throughout the day, I'm going to see the sun move across the sky. And then in the evening, I'm going to see the stars moving across the sky. Meanwhile, I'm sitting at my campfire or I'm sitting under a tree and nothing else is moving. So it kind of makes sense that the Earth would be the center of everything. So for the geocentric model, the Earth is the center of the solar system and everything revolves around the Earth. The next model that comes along is called the Greek celestial model. And this comes about with the discovery of planets. As we start to notice more and more planets, we need to put them on their own spheres. And so for the Greek celestial model, it is a type of geocentric model. The Earth is still the center, but the Earth itself has its own spheres that go around it. And so the planets go around on their own spheres, the stars have their own sphere, the sun has its own sphere. The first scientist we're going to talk about is Aristarchus, and this is around 200 BCE. Aristarchus actually was the first person, not Copernicus, but Aristarchus was actually the first person to state that he believed the sun was the center of the solar system, and that this was because he did some calculations and he figured out that the sun was actually much, much larger than the Earth and therefore would probably have everything going around it instead of going around the Earth. Aristotle in 384 to 322 BCE actually was the person that came up with the whole idea that the Earth is imperfect and the heavens are perfect. And this actually leads to the formation of the belief systems or the doctrine for the Roman Catholic Church. Okay, he was also, though, the first person to actually show experimentally that the Earth is actually a sphere. And he did this by looking at the moon phases. I'm sorry, not the moon phases, the eclipses of the moon. And so what he did was he looked at the shape of the eclipse and the shadow of the Earth as it moved across the moon, and it was always curved. And that gave him this idea that the Earth must be a sphere and not flat. Again, he also proposed that the laws of heaven were not the same as the laws on earth. He also estimated the size of the earth and the moon and the sun with respect to one another. These calculations were a little bit off, but they gave us a really good idea of the relative sizes of these objects. Okay, so next is Hipparchus. Hipparchus lived between 190 and 120 BCE, and he was actually the first to come up with a star catalog, which was pretty intense. He actually also determined that the sun and the moon travel a circle with the Earth near the center. He actually also figured out eccentrics, which is that there's some eccentricity or some elliptical nature to these paths. This also led to the Ptolemaic model, which we're going to talk about in a little bit. And that's right now. Okay, so Ptolemy lived about 140 AD or CE, which is Common Era. He actually developed epicycles to describe what we call retrograde motion. I'm going to have a link available for you in the course so that you can see what a retrograde motion would look like. It's actually the apparent backward motion of the planet. So basically, the planet will move like this. It goes this way, and then this way, and then this way on the sky. And so in order to describe this, the only way to do that was what we call epicycles. And basically, Ptolemy decided that these planets move in circular orbits, and these circular orbits also move around the Earth like this. Okay, so it was kind of complicated. The model was very complicated, it was hard to explain, and so it really should not have lasted that long, but it did last until the 1500s, which is surprising. I think it's because a lot of people just didn't want to think about how else to describe this. It didn't make sense unless you looked at the Earth not being the center. So that brings us to the heliocentric model. Remember, we had already mentioned this, that the heliocentric model was actually proposed in 200 BCE. Now we get to the point where we're in the 1400s, 1500s, and we're starting to get more and more observations, which are telling us that maybe it's not an Earth-centered system after all. So the heliocentric model is defined as the sun being the center of the solar system and everything orbiting around the sun. This was a problem because the church, which happened to be the government at the time, had accepted Aristotle's view that the earth is not perfect, but the heavens are perfect, and that we are the center of God's creation, and therefore everything goes around us. Well, now if we take a heliocentric model, that's not the case anymore. And it kind of puts a bummer, pretty much. This doesn't work. It becomes heresy with the church. And remember, again, the church is the government. So between 1473 and 1543 is the life of Copernicus. He actually finds this work from Aristarchus and says, whoa, this makes a lot of sense. It cleans up a lot of the problems with the Ptolemaic model. And so he actually does some research on this. And with some data, he actually proposes the heliocentric model to his friends. He does not do this publicly because heresy can be punishable by death. And so he does not want to die. Who does? And so he holds off on publishing his work. So it turns out that the heliocentric model is simpler than the Ptolemaic model, which really is a great benefit to the model. It does explain retrograde motion, because if the sun is the center, then we can easily have one planet bypassing another, and that would give us that same pattern of retrograde motion. The problem, though, is that Copernicus still uses circular orbits to describe the planet's motions, and this gives us probably like a 12% error in the actual observed data versus the predicted paths of his model. Because of that, he still uses epicycles in his calculations for his model. He writes this in a book which he names On the Revolutions of the Celestial Orbs. Now, he doesn't publish this right away. He waits until he's on his deathbed. And then with the coaxing of his friends and colleagues, he actually publishes this book. It causes a huge stir. People are outraged. Other scientists are saying, you're crazy. This is a crazy idea. The Earth is the center of everything. And so politically, it was also a bombshell. But scientifically, this caused a breaking apart of groups. So we have scientists that were like, yes, Copernicus is on board. This is great. This is exactly what it is. And then we have those that are still following the geocentric model. And it causes a scientific revolution. And in fact, our definition of revolution, an uprising against, actually comes from the title of this book, where it says, On the Revolutions of the Celestial Orbs. So the word revolution here takes on a new meaning, which we now use for revolutionary wars. Okay, so Tycho Brahe says I don't buy this. I don't buy the heliocentric model. I'm gonna build an observatory. He was Danish nobility, so he had the power to pull strings with the king and get some financing, which he does. He builds an observatory to collect data to verify the geocentric model. And so he does that. He gets those precise measurements, but he has so much data, and it's difficult for him to get it all analyzed, so to speak. So eventually what he does is he hires a young man by the name of Kepler, Johann Kepler, to analyze that data for him. He also makes observations of supernovae and demonstrates that they have to occur farther, much farther away than where the planets are located. Sad story about his death. It turns out that when Tycho Brahe was young, he actually was in a duel and his nose got sliced off. And so he ended up having a metal plate or wax nose that was put on there. We're told from history that he frequented prostitutes and he ended up getting syphilis. Recently, studies have shown, they've done some more research on him, that he actually died of a bladder infection from a party that he was at. It turns out that if you went to these parties with the king, you could not get up to go to the bathroom until everybody was done. Turns out he really had to go, but he had to hold it, and he ended up with a bladder infection, which ended up killing him. Before this new idea or this new evidence, historians believe that Tycho died from either syphilis or from alcoholism, liver cirrhosis, which he also had at the time of his death. I think with a metal nose, I'd be drinking too. Just saying. Okay, also 1577, he observed a comet and he showed that this was well beyond the moon. This was actually kind of interesting because up until this time, comets were believed to come right close to the Earth, in between the moon and the Earth. He was one of the greatest astronomers to hold to the geocentric model. He was the last one, actually. As far as the great astronomers are concerned. And there's a reason why he believed in the geocentric model, and this is because of the parallax. Parallax is caused by you viewing an object very far away from two different locations. And basically, he said that if we were not the center, we would see parallax between the year. So for instance, in September, we would look at something and 6 months later, we would look at it again and it should have shifted, but they didn't. The planets didn't shift. And so Tycho said, because there's no parallax, this means that the Earth has to be the center and not the sun. Well, here's the problem. He's looking at very close objects to do this, okay? So if you take your finger and close one eye and line this up, I'm going to line it up with the screen so you can see my finger. Okay, so here's my finger, and I'm lining it up with one finger, one eye, okay? Now, if I look at it with the other eye, it shifts the background, okay? That's the parallax. And because Tycho didn't see that, he said that the geocentric model could not have been the correct model. Okay, so now on the scene is Johann Kepler. He's hired about 2-3 years before Tycho dies. And basically what he is hired to do is he's hired as an apprentice to analyze the data. Upon Tycho's death, his family wants all of the data and all of the experimental equipment in the observatory. Kepler refuses. He holds on to it. He goes to court. He loses in court, but he still holds on to the data. It takes him about 10 years to analyze that data. And in that time, he still cannot make this data fit the geocentric model. Now, keep in mind, that these data points of the planets, their motion, have been accurately recorded by Tycho. So there's nothing wrong with the data. It's very accurate data. But it takes Kepler a long time to figure out what's going on. And when he does, he comes up with the 3 laws of planetary motion. Okay, so he spends those years analyzing the data. The first law that he comes up with is that planets travel elliptical paths with the sun at one focal point. The second law he comes up with is that planets sweep equal areas in equal amounts of time. And basically what this says is that planets will speed up as they get close to the sun, and they'll slow down as they move farther from the sun. The third law is kind of complicated, and it took him a while to figure this one out. If you take the time period of a planet and square it, it's actually proportional to the distance between the sun and that object cubed. How he came up with that, I don't know. He's a genius. His name's in the history books, mine is not, and that's why. Okay, so basically he determined that p squared is equal to a cubed times some proportionality constant k, which by units wise we make it equal to 1. Okay, so p is the period in years, and a is the average distance from the planet to the sun, which is measured in what we call astronomical units. And hopefully you covered that in the first chapter. Astronomical unit is the distance, the mean distance between the sun and the earth, which is about 93 million miles. Okay, I'm going to also have this link available at this time. You want to pause your video and you want to go ahead and click on this link and take a look at the 3 laws of motion, the 3 planetary laws. Okay, next on board is Galileo Galilei, and he is actually a very interesting guy. In 1609, he actually makes observations with a telescope that was actually discovered by a Dutchman by the name of Johann Lippershey. And so he makes this telescope and he actually starts looking at the heavens. And these observations actually support the heliocentric model, and a couple of these observations actually knock out the geocentric model completely. Now, there's a plot twist to this. Galileo's best friend is the Pope. His daughter is actually a nun. So that makes it a little bit interesting. So basically what happens is he looks at the moon with his telescope and he finds that it has features very similar to the Earth. It has mountains, it has lava pits, it has craters, all kinds of interesting things. But here's the problem. The heavens are perfect. The Earth is not. If the moon, which is in the heavens, looks like the Earth, we're kind of blowing a hole into that theory that everything in the heavens is perfect. So that's one notch for the heliocentric model. Next, he takes a look at the sun with his telescope and he noticed that there's these black blotches on the surface of the sun. He finds or notices or discovers sunspots. This, unfortunately, for Galileo, is also why we know not to look directly at the sun, and especially not to look at the sun with a telescope without a solar filter. He actually ends up going blind because he was focusing all of that sunlight and that energy into his eye, which caused early cataracts. He also found the moons of Jupiter, the 4 largest moons at least, and they're actually named for him, the Galilean moons. He watched them, he recorded their positions over a long period of time, and here's the thing. If the Earth is the center of the universe and the center of the solar system, we shouldn't have things going around other planets. They should only be going around the Earth. So this is another indication that the heavens are not perfect and that the Earth is not the center of everything. The next observation he makes is of Saturn. He notices that there's these little blobs on the side of it. In other words, Saturn is not a sphere. It's not perfectly shaped. What he was actually seeing was the ring system of Saturn. He also noticed that there were more stars in the sky than he could actually see in his telescope. I'm sorry, he could see them with the telescope, but he couldn't see them with the naked eye. So that tells us that there's more stars out there than we can see with our eyes. And why would God hide them from us? That was his thought. Next, and this was the cincher, phases of Venus. He actually observed Venus through all of its phases. Here's the thing though, if Venus were going around the Earth, we would never see all the phases that we see like with the moon. So he was able to actually show from new Venus all the way to full Venus through the crescent, quarter phase, and gibbous phase, and then all the way back again to new Venus where we didn't see it at all. Okay, those phases are not possible with a geocentric model. Now, what did Galileo do with all of this information? Well, he wanted to tell everybody, but here's the thing, his best friend's the Pope. So he goes to the Pope and he says, hey, I want to write a book about this. And the Pope says, oh, no. Geocentric model is the model. This is the church doctrine. Blasphemy, death for you. I don't want to have to kill you, but I will. So Galileo says, okay, well, what if I write the book as scientists talking to one another, and I make sure that I include this information and just make it sound like, you know, the geocentric model is the model and the heliocentric model is not true. So his friend says, sure, no problem. Well, Galileo didn't do that. He actually wrote the book, and he showed all this evidence to prove the heliocentric model. His friend had no choice. He put him under house arrest at least. But Galileo became very ill under house arrest, and he was never the same since. He actually did recant in order to be released from house arrest. And then later on, he said, you know, the heliocentric model is the model we need to follow. So he was willing to go through quite painful experiences for his beliefs in this model. Okay, now Sir Isaac Newton comes along from 1642 to 1727, and he wants to prove Kepler's laws of planetary motion mathematically. He actually develops calculus to do this. And so in doing so, he actually comes up with the laws of motion, which we still use today. So the first law states that things in motion will stay in motion, things at rest will stay at rest, unless acted upon by some net force. Now, when we say things in motion stay in motion, we're talking about a straight line path. But planets don't travel straight line paths, they travel elliptical paths. And that means there has to be a net force acting on them. Okay, so if there's a net force acting on them, that means that something has to be doing that. Okay, and so Newton was able to figure out that it's probably the gravitational interaction between the Earth and the Sun. The second law states that if there is a net force, that net force is going to be equal to the mass times the acceleration of the object. Notice there's a little, it looks like a big, huge E-ish kind of character. That's a sigma, and that means sum of. So we're adding up all of the forces acting on the object to get a net force. Okay, so here's a little cartoon for you. He pushes the ball up the mountain. The bear says, I'm strong, I got this. And then things in motion stay in motion, it keeps going. So same thing in space. Things in motion stay in motion. If you have something that starts moving in space, it's going to keep moving. If you have things on Earth that you push, they're going to keep moving unless some net force acts on it. So what happens on Earth is things slow down because of friction. Okay, I'm going to make this website also available. So at the end of this slide, you want to go ahead and pause and take a look at the interactive website for Newton's laws. It's a little bit kid-ish, so keep that in mind. It's not adult level, but I thought it was appropriate for at least giving it a nice, cute spin. The third law states that for every action, there's an equal and opposing reaction. That means that forces act in pairs. If I push you, you push back. If I lean against the wall, the lean pushes on me back. Or the wall pushes back on me. If I'm sitting in a chair, the chair's pushing up on me. Basically, we call those touching forces. Planets act on each other gravitationally. We call those field forces. Okay, the last thing we're going to talk about for Sir Isaac Newton is his law of gravitation. And this actually irked him quite a bit because he could not describe why. All he could do was come up with this law of gravitation. Okay, so basically he states that the force of gravity is an attractive force between two objects with mass. The force is directly proportional to the product of the masses. That means mass 1 times mass 2, divided by the distance between them squared. 1 over d squared is called an inverse square law. And it turns out that all of our natural laws tend to be inverse square laws. The farther away you get, the less the field gets by 1 over d squared. So I'll give you an example. If I'm 1 meter away, I have a force of F. If I go 2 meters away, that force decreases to 1/4. If I go 3 meters away, it's 1/9. 4 meters away, 1/16. What about 5 meters away? That's right, 1/25. So you see that force decreases by 1 over d squared as you move away. Let me tell you another thing about Sir Isaac Newton. It's stated somewhere, probably in the Newton paparazzi of that time, that on his deathbed he stated that his greatest accomplishment was dying a virgin. It turns out that there's quite a bit of evidence that shows that Sir Isaac Newton was gay. He was also part of the church. And so he did not partake of his feelings. He did have mutual relationships with other men as far as communicating, talking with them, but he never had lost his virginity. And so he stated on his deathbed that that was his greatest accomplishment. Now for Albert Einstein. Isn't he a ham? He lived from 1879 to 1955, and he revolutionized our idea of space and space-time. He came up with 2 theories we're going to talk about, the theory of special relativity and the theory of general relativity. By the way, he did not win a Nobel Prize for either of these. He actually won his Nobel Prize for the photoelectric effect, which is actually the reason we have DVDs and video cameras. Okay, so what is special relativity? It's broken up into 2 postulates. The first postulate states that observers can never detect their uniform motion except for the fact that there's some reference frame. Excuse me. So without a reference frame or somehow some way to compare it to something, you can't take a measurement. So if you're in a black box, well, with lights inside, and you don't have any windows, you can't see outside, you have no idea if you're moving or not. So that's basically what he says in that one. He also states in the first postulate that the laws of physics are the same for all observers. That means if I'm in a moving train and you're standing on the side, we both have the laws of physics being obeyed in both of our reference frames. In other words, me on the train and you on the platform. Now, here's the kicker. This is only true if you're not accelerating. So a lot of people say, oh, I've seen an article where he says you can't go faster than the speed of light, but this experiment shows you can. Well, sure you can, as long as you do not follow this first postulate. I mean, if you're in an accelerated reference frame, these laws don't obey. I mean, this postulate is null and void. That's why we have the statement that you have to be in a an inertial reference frame. If you are in a non-inertial reference frame, this doesn't work. Okay, so a lot of times people think that laws are broken, but they're not. They're very specific in what they say, and as long as those things are held in place, it works. If you don't do what it says, then of course it doesn't work. Okay, so that's his first one. Basically, you have to have a reference frame, and two, you cannot be accelerating for either reference frame. Next, for the second postulate, he says that the speed of light, actually the velocity of light, because it depends on direction, is constant and will be the same for all observers independent of their relative motion to the light source. So basically, if I'm sitting here looking at the light has a speed of 3 times 10 to the 8 meters per second. If you are riding on that light beam, the light you see is traveling 3 times 10 to the 8 meters per second. Okay, it gets tricky because the speed of light is constant, but your space-time is not. And that's how we get things moving slower as they go faster. Okay, so the time is the difference, not the speed of light. Okay, so here's a picture of his general theory. The general theory of relativity basically says that mass tells space-time how to curve, and the curvature of space-time tells us how it accelerates. So basically, objects with mass will deform space-time, so that as you get closer to that curvature, time also stretches. Okay, so as you move faster, the stretching causes time to slow down. So time is not a constant. And that's how we get the speed of light to remain constant, no matter what reference frame. If our time slows down and the speed stays the same, then the distance changes. And that's how we get around it. So in physics, or at least in astronomy, when does that become important? Well, when we have really large gravitational objects like galaxies and such, we actually see what we call gravitational lensing, which is the bending of the light as it goes around the object. Okay, that gravitational lensing has been observed, but we can't figure out what's causing it. Okay, Einstein's general theory of relativity tells us that the space will curve around those massive objects and light will travel along that curvature. In other words, space-time is telling it how to accelerate around. Another way we see it is with black holes. As we get closer to the event horizon of a black hole, time actually slows down. At the event horizon, time stops. Okay, so for us as an observer watching them, their time slows down and stops. For them, they see us speeding up. Okay, so it's kind of weird. If you want to get an actual idea of how that looks, there's actually let's see, it's an SG1 video. It's called A Moment of Time. It is fantastic in showing that time dilation that occurs at the event horizon of a black hole. I'm fascinated by how that works. Another way, what's the other one? Interstellar. If you watch Interstellar, that will also give you some idea about time dilation and how it works.